We've now seen binary search written in two ways. We've written it imperatively, and we've written it using a recursive function, a more functional way. But how much work does a binary search actually do? And what is the order of a binary search? We know the sequential search is order n. We've talked about the sorts that we wrote being order n squared. The binary search is definitely faster than the sequential search, but how much? Well, in order to understand this, it helps to think about, we have a whole bunch of numbers here. We have n numbers. And after we've done one comparison, we're able to cut it down to half that, so n over 2. And then we do one comparison there, and we cut it down to n over 4. And we do one comparison there, and we go to n over 8, etc., 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 until we get down to where we have 2 and then one element. And at that point, either we do a comparison and it matches, or it doesn't match. And we can either say it's there or it's not. So we do one comparison at every level here. So the question is, how many levels are there? Well, instead of going from the top down, I think it helps to go from the bottom up. We have 1, 2, and then it would be 4, 8, 16. So basically, every level has 2 raised to the power of L. And we want to find out what value of L would make this equal to n. So how many total levels are there in here, so that we wind up building up to the full number of things in our array. Well, if you remember a certain level of math, you know that this can be solved by taking the log of both sides, and we get that L is equal to the log base 2 of n. Turns out that when we're talking about order, we throw away the base for the logs, because it turns out the only difference between logs of different bases is a constant multiplicative factor, and as we said before, we throw that out when we're talking about order. So the binary search is order log n. Well, okay, sounds nice. How good is that? Well, it's worth kind of making a little table for describing what this does. And first, we'll start with one handy little fact to remember. 2 raised to the power of 10 is roughly equal to 10 raised to the power of 3. Okay, 2 to the 10 is actually 1024, and this is 1000. But they're pretty close. So if I have then 1000 elements, how many comparisons do we have to do in order to, if we're using a binary search? Well, since this is 2 to the 10, roughly, that means that we have to do 10 comparisons. Our sequential search would have had to do, if it was there, on average 500. The binary search will have to do 10. Okay, and the 10 is actually the worst case. It could stop before that. That seems pretty good. But it gets better. What if we didn't have 1000 elements, but 1,000,000 elements? How many comparisons would we have to do then? Well, it turns out it only grows to 20 comparisons in that case. And this is the real power of logarithmic growth. The log function is a very slowly growing function. What if instead of 1,000,000, we had 1,000,000,000 elements? Okay, this would be a very large array. That's a lot of data that we would have there. But if it were sorted and we were using a binary search, we would only have to do roughly 30 comparisons in order to be able to find the value that we were looking for. Okay, so the binary search is much, much, much faster than the sequential search because this logarithmic growth is very slow. Okay, and it's especially pronounced when you get to very large data sets. So this is why it's very helpful if you're going to be doing a whole lot of searching. While a sort can be costly, if you're going to do a lot of searching, it actually makes sense to do the sort once so that then all of the searches will be much, much faster than they would have been otherwise.